All right, guys, we're going to start our new chapter with an introduction to conics. And really, when we talk about conics, the first thing we talk about are circles. Okay, so we're going to review the things you guys learned about circles from back in geometry. So our second to last chapter of geometry deals with circles, the final one with trig. And really, both of those things lead into pre-calculus very nicely. We've already done a lot of trigonometry. And here we'll talk and open up our conic sections chapter, which is chapter 11 in the text, with a review of circles. We're going to go through this pretty quickly, other than maybe one thing algebraically that you guys haven't seen before. So if you remember from geometry, the standard equation of a circle is x minus h squared plus y minus k squared equals r squared. Okay? And h comma k would be our center, with radius r. So whatever number would be on the other side of this equals sign, we could take the square root. That would be the length of your radius, okay? Remember the definition of a circle, okay, before we go any further, is the set of points a fixed distance from a fixed point in space. All right, so when we talk about the definition of a circle, many math students look at it as a circle. Okay, those students who really feel that deeper connection to math not only look at it as a circle, but they look at it as a set of points. So let's say we have this fixed point in space, and I said, all right, I'm going to draw all the points that happen to be a distance of, 1 inch away from this. So if I go about an inch, and I put a point. Go an inch, put a point. Go an inch, put a point. Put a point. Put a point. Put a point. What you would be seeing is that if I put every single point, all infinite amount of them, on this paper that were exactly 1 inch from that fixed point, it would end up forming the shape of a circle. Now that's a freehand circle, so obviously it's not perfect. That fixed point in space becomes the center of the circle. That distance that each one of these points is away from the center becomes our radius, okay? So what do we need to write the equation of a circle? Well, obviously we need the x-coordinate of the vertex. We need, not the vertex, the center. The y-coordinate of the center and the radius. This problem should be as simple as any. Plug them in where they go. I'm going to take the liberty of changing this minus 5, this minus k, minus a negative would lead to a plus. R is 7, r squared would be 49. Done and done. You guys did that a lot in geometry. Okay. Example 2, write the standard equation of a circle with center -1, 4 that passes through the point 3, 8. There's two ways to do this. I'm going to show you one way and talk about another way. Okay. So this is going to be our h and our k. Remember, the x and the y of any equation represents any point on that graph. So if this circle passes through the point 3, 8, that would be representative of one of the x, y coordinates. Okay? The one thing we don't have here that we need is the radius. So let me rewrite our equation here. I have h, I have k, I have x, I have y. That will leave us only with an r to solve for. So x minus h squared plus y minus k squared equals r squared. I get a 4 squared plus a 4 squared equals r squared. I get 32 equals r squared. To be honest, we can stop right there because we're actually looking for r squared if we're creating an equation. Could I take the square root of this? Sure. Would I then have to square it when I put it back into my equation? Yes. So let's be efficient and not do that. How do I write this officially? With the h and the k, let's leave the x's and y's as x and y, and I'll plug in my 32 for r squared. So we get x plus 1 squared plus y minus 4 squared equals 32. That would be the equation of the circle with center -1, 4 passing through the point 3, 8. How else could we have done this? We could have used the distance formula with these 2 points, because the distance from the center to any point on the circle would be equal to the radius. So you could have done that as well. All right, example 3 was the one that I was talking about at the start of the notes, where the algebra here you may have never done before. Okay? And this asks that for the center and radius of the circle with this equation. Now the problem here is this equation is not written like our standard form. I don't have some binomial with x squared or some binomial with y squared, and I don't have just a number on the other side. Okay? So the strategy for working with something like this that you'll see when we, with our circles review, you'll also see when we get into ellipses, which is our first conic section of chapter 11 that we talk about, is what we call completing the square. Some of you may have seen this in A2T or A2TH last year. Hopefully a lot of you have. Okay? So completing the square means we're going to take the terms that have the x squared and the 6x, and we're going to leave room to add a constant that would make that a perfect square trinomial. Then we're going to take the y squared and the term that contains a y, get them together, leave room to add a constant that's going to make that a perfect square trinomial. So the first thing we have to do here is get our y squared over to the side that contains not only the negative 4y, but also the x squared and the 6x, because we're trying to get this to look like this. That's the goal of completing the square here. So I'll rewrite over here, x squared plus 6x, let's write it in proper form, plus y squared minus 4y equals 8. So I feel like we're in a better situation now, right? We're looking to get it to look like that, and now at least we have our x's, we have our y's, then we have our constant, our number, on the other side, okay? All right, now what I said was we need the group of x's to end up being a perfect square trinomial, so we can technically factor it and get it to look like something like this. We'll do the same thing with the y's. All right, so here's what we're going to do. We're going to leave room to add the number that will do that for us. We're also going to leave room to add the number that's going to do that for our y's. At the same time, we know algebraically that anything we need to do to one side of an equation, we have to do to the other side. How do we know these are going to be positives? Well, to get a perfect square trinomial, we're going to have pluses here, because a negative times a negative is going to give us a positive, and a positive times a positive is going to give us a positive. Okay? All right, so how do I know what number is going to give me a perfect square trinomial here? Basically, that when I factor that, it's going to give me one binomial squared. How do I know how to do that? Same thing here. What number, along with the y squared and the negative 4y, is going to give me some binomial squared? Not like two different factors. Okay? There's a numerical way of doing this. Okay? You would take the middle term, if you consider this the leading term and the constant, you would take our middle term, divide it by 2, and square it. 6 divided by 2 is 3. 3 squared is 9. So I'm going to add a 9 here. I'm also going to add a 9 to the other side. Okay? Then, take the middle term, divide it by 2. I get negative 2, square it. I'll get a 4 here. Now, if you really want, you can like check your own work. Let's not assume it's correct. All right, let's think about how we would factor this. The two numbers that add up, that multiply to be 9 and add up to 6, that would be 3 and 3. So our two factors would be x plus 3, x plus 3. We did exactly what we wanted it to do. We created a perfect square trinomial so that when it was factored, it turned into one binomial squared. Why did we want that? It's because we're trying to get the equation to be in our standard equation of a circle. We need a binomial squared here. Same thing down here. How would we factor this? Well, the two numbers that multiply to be 4 and add up to negative 4, that would be two negative 2's. So we'd have y minus 2 times y minus 2, or y minus 2 squared. On the other side of the equal sign, 8 plus 9 plus 4, that's 21. We now have this circle in our standard equation of a circle form. Here's your h, here's your k, opposite of signs. Here's your r squared. Okay, so what is the center of the circle? This circle would have center negative 3 comma 2. Remember, opposite of the signs, because we have minuses in our standard equation. And the radius would be the square root of 21. r squared, square root, can't be simplified. All right, let's move on to our last example here. Graph the solution of the following inequality. Now, same type of equation here. It's an inequality, same type though, where we're going to need to complete the square. We don't have this written in the standard equation of a circle. We need to do some algebra to make that adjustment. So how are we going to do that? Let's get our x's and our y's on the left side by subtracting the 8y. At the same time, I'm going to leave some room to add in that constant that we're going to need. On the other side, we've got an 8. Cut this in half and square it. That would give you a 1. Cut this in half and square it. That would give you a 16. Factor my x squared minus 2x plus 1. That is a perfect square trinomial. We'd get x minus 1 squared. Factor my y's. That would factor to y minus 4 squared. 8 plus 1 plus 16 happens to be 25. There's your center, 1 comma 4. There's your r squared, meaning the radius is 5. We can put this on the graph, no problem. Just like your geometry teacher asked you to do, let's plot the center. 1, 1, 2, 3, 4. Let's plot the radius points in each cardinal direction. So we'll go 5 to the right. 1, 2, 3, 4, 5. 5 up. 1, 2, 3, 4, 5. 5 to the left. 1, 2, 3, 4, 5. 5 down. 1, 2, 3, 4, 5. And let's create our best freehand circle that we can. I am extremely good at creating freehand circles. Don't be upset if your circle doesn't look as cool as Mr. Newberger's. I might be the best freehand circle drawer on earth. Okay, there's a ranking. Okay, you guys can check it out. freehandcircledrawers.com. Okay, there's a top 10 list. I'm number 1. All right. Now we did say that this was an inequality. And from algebra and algebra 2, you should know that when we graph the solution to an inequality, it's really a set of points, a shaded area, if you will. Okay? What this means, and I'm sorry, these really should be greater than signs. Okay? When we have a greater than sign and we're dealing with in a circle, what the greater than sign means is all the points, okay, greater than, should lead us to all the points further from the center than the radius. Or I guess than the length of the radius. That's what greater than means in terms of an inequality with a circle. If it was a less than, that would mean all the points closer to the center than the length of the radius. So greater would mean we want all the points outside of the circle. Okay, further away from the center than 5. Every one of these points are a distance of 5 away from the circle. I want all of these points. The solution to an inequality is always some sort of shaded area, some sort of infinite amount of points. Okay? This shaded area is the solution to this inequality. All right, I know there's one final example. We'll do that at the start of class to give you a little bit of a challenge with some algebra and with remembering circles.